All right, let's try this. You guys can thumbs up? Everybody can hear me? Sweet. Okay. Welcome to Ocean Studies Seminar this afternoon. I'm going to do a quick introduction for our speaker. Before I start, I just want to check to see if anybody else has any announcements before I make several. Okay. General announcements for this afternoon. So the department is hosting dinner for Laura at 5 after the talk. Everybody is invited. If you're not on meal plan, the department will cover, right? So don't let that be a reason not to come for dinner. Secondly, there is another presentation that's going to be happening here at 4, right when we're done. So we're going to try to be really efficient about getting our stuff kind of cleaned up and out of here on time. Okay? All good? Okay. It is my complete pleasure to introduce our speaker this afternoon. Dr. Laura Reiser Wetzel, rhymes with pretzel, boom, is a professor of Marine Science and Geosciences, and she teaches at Eckerd College. She joined the Eckerd College faculty in 1997. Dr. Wetzel enjoys teaching a wide range of subjects, from introductory geological oceanography courses to upper-level classes in mineralogy, structural geology, and geophysics. She has taken students abroad for field courses in the Galapagos, in Iceland, and to the Bimini Biological Field Station in the Bahamas. She studies mid-ocean ridge tectonics and is particularly interested in submarine hydrothermal systems. Before teaching at Eckerd, which is itself a small liberal arts college in St. Petersburg, Florida, she earned a bachelor's degree at Beloit College in Beloit, Wisconsin, and that was, I believe, a double bachelor's, right? Geology and physics. Mm-hmm. So a shout-out moment for undergrad Midwestern geology. Mm-hmm. N equals 2. And then her doctoral degree at Washington University in St. Louis, Missouri. And so with that, I turn the floor over to you.
Oh, applause. I love applause. That's great. Yes, whenever you meet a fellow Midwesterner, especially a geologist, you gotta celebrate. Anybody here from the Midwest? Yay! Excellent. See? Small but mighty group. Excellent. Oh, also very good. Good.
Where's the Midwest?
The Midwest. Ooh, good question. So we've got Minnesota, Wisconsin, Michigan, Illinois, some might include Indiana, Iowa. That's what we consider the upper Midwest. Around the Great Lakes. Think Great Lakes, but on the western side, central and western side of there. So, so I am hopefully going to reveal some things about plate tectonics that you perhaps already knew, and then some things that you don't know, hopefully. If you knew it all, then maybe you wouldn't need me. So plate tectonics is not perfect. So a little bit about me first. So I like rocks, volcanoes, and earthquakes. That's what I really find interesting. I grew up in Wisconsin. We mentioned that. I went to Beloit College. We mentioned that. That's when I first saw the ocean, when I was in college. I drove with a friend to Boston Harbor, saw the ocean, stayed in Boston overnight, and drove back. That's the first time I saw the ocean, and now I see the ocean every day. It's amazing, and you all have seen the ocean probably from a much younger age than I did. I got a PhD from Washington University in St. Louis. Thank goodness I went there for a summer because it's really hot there during the summer, and I don't know that I would have made it in St. Petersburg, Florida without experiencing a series of St. Louis summers. So fortunately, Eckerd College hired me, my first and only job after graduate school, and there I teach in the Marine Science and Geosciences programs. So one of the things that's big at Eckerd is global education, and so yeah, I've taken groups to the Galapagos a couple of times, and then this last summer I took a group of 16 students to Iceland for 2 weeks. And if you're a geologist, oh my gosh, oh, it's just one of the most amazing places, but Maine is too. Maine is pretty amazing. And this is my first trip to Maine. So I'm really excited to be here. I came a day early to go over to Acadia National Park. Thank goodness the shutdown did not shut down the park. And I got to go up on Cadillac Mountain. Oh, I would have included slides if I had time, but You all have probably already been there, but I'm really excited about that. Here's me in Iceland. Here I climbed a cinder cone, and here I'm in front of some columnar basalts. Oh my gosh, columnar basalts, also awesome. They occur when a lava flow then solidifies from the outside in and then makes all these columns. Those are natural columns. And now that you've seen those, you've seen them before, haven't you? You've seen them in video games, you've seen them in movies, you've seen them on album covers. They're all over the place. So now you know they're actually real. They're actually real. Ooh, How to Train Your Dragon, if you've ever seen that movie. One of my favorites. They're also in there. All right, so this is where I spend most of my time at Eckerd College. So you have water around your campus. I have water around mine too, except it's the Gulf of Mexico instead of the Atlantic Ocean proper. And we have a little creek that comes out, and this happens to be my building right here. Yeah, it looks like a stealth bomber or a stingray, whichever one you want. And my office is right over here. I get to overlook the water all the time. But you guys get to see that too. Just mine's a little bit warmer most of the time. You had a beautiful day today. Oh my gosh, I mispacked. Should have worn some lighter clothing. But it's a beautiful campus. It's a small liberal arts college, so we have a very different set of curricula than compared to yours. But we have a waterfront program. We have a program that's affiliated with the Coast Guard. And Marine Science is the largest major on campus. So here I am, also to look at your facilities and your ocean studies programs. So, but what do I do my research on? I said, do you want to talk on hydrothermal vents? I haven't done any research in that area for a while. Or do you want my more recent stuff on plate tectonics? And I said, well, your more recent stuff. So we're going to talk about plate tectonics. Hydrothermal vents are cool too, but another day. You'll have to have me back another day to talk about that. So my first paper in graduate school, was this one, Evidence from Earthquakes for Bookshelf Faulting at Large Non-Transform Ridge Offsets. In 1993, I know that was a long, long time ago. And science was in a very different place than it is now. It took me 3 years to do this paper. We're going to find out that you can do the same thing in about 3 months now. So I worked with a student this last summer, actually summer of 2024, to basically update this study. So we're going to go through the update to this. But before we do that, let's talk a little bit about theories. Okay, so a scientific theory is a well-supported explanation of our world. It allows for predictions. So you've probably heard of a few of these theories. So what's this one? Newton's theory of? Gravity. Just, yeah, yell it out. I don't want to. What about this one? Einstein's theory of?
Relativity.
Oh, yeah. Everybody else got that too? Now you're going to be quiet for this next one, okay? Let everybody else answer. Yeah, I know it's hard. How about this one? Oh, also in the first row here, we've got Big Bang Theory. Okay, so these are all theories. These are physical theories, right? But we also have some that are in the kind of the natural, more natural world. Somebody from over here, what's this one? Darwin's theory of evolution. Great. And what's this one? Guys over there, people over there. Plate tectonics, exactly. The theory, oh yeah, excellent. We got the theory of plate tectonics. So of all of these theories, the theory of plate tectonics is the most recent one. The term was coined in the 1960s, so about 60 years ago. And so it's still an evolving theory, right? Because theories are also meant to be updated. So hence the title of my talk, which is Plate Tectonics Isn't Perfect. Actually, none of these theories are perfect. We're always updating these theories because it's science. We always get new information to make things better. More important. Or not more important, but better predictions of the future. Okay, so what is the theory of plate tectonics? This is one of the few definitions I put up in my classes to actually have people write it down because I think it's really important. You don't have to because you're not going to have a test on this, but it's the formation, destruction, and motion of segmented sections of Earth's surface called plates. Okay, so why do we call them plates? You're at a picnic. You have a plate. What do you want in your plate? You want it to be nice and rigid and not floppy, right? You don't want one of those cheap dinner plates. Oh, that's what we got for our pizza last night. Was one of those little floppy plates that you can't carry that around. You need like 3 of them because you need something that's really nice and thin, but yet is very strong. And that's what the tectonic plates are. Hence the term plate for this thin, very strong section of the Earth. And those plates are constantly formed at the spreading centers. They're constantly destroyed at the subduction zones and at mountains. And then sometimes they just slide past each other. They move around. Okay, so hopefully that's not news. You knew all of that. I hear you've had to take like a physical geology class and maybe even a geological oceanography class. So all of that should actually just be a review so far. But we're still gathering data, right? Plate tectonics isn't perfect, so I like to gather data about plate tectonics. Let's see what I found out. Oh, I was sitting this summer, August 26th, there I am, looking up the earthquakes that happened in the world, and then I'm like, wait a minute, what the heck is that? Zoom in. Whoa, it's right there. Okay, zoom in some more. Because that was today. That was the day I was putting this together, because I like putting together PowerPoints. Not everybody does, but it's one of my favorite things to do. So this summer I was putting together this PowerPoint for here, and then I was just like, oh, holy cow, there's this earthquake. How many of you knew that an earthquake happened here a few weeks ago, about a month ago? Oh, good, excellent, good for you. So there's this shallow earthquake that occurred not very far away from where you are. One of the hydrophones that Dr. Bear oversees actually recorded it, so we've got a nice acoustic record of it. And it turns out this area has small earthquakes about twice a year. And these earthquakes are along old faults that were created a very long time ago, but there's still cracks. So there's still weak spots in these plates. And so these earthquakes occur along these weak spots. And so these faults were probably created, when the Appalachian Mountains were created. Those continents collided, and they caused a lot of faults, a lot of breaks in that crust. And then after the Appalachians were created, millions of years later, the Atlantic formed to break up Pangea and break up the dinosaurs too. Okay, so there's a little tiny one in Maine. Well, I was also studying some pretty small ones, but along plate boundaries. So most earthquakes, unlike being in Maine, most of them are not in Maine. Maine's pretty far from a plate boundary. Most of them are along plate boundaries like this one, the San Andreas Fault. You may have heard of it in California. And then, so that is a plate boundary we call a spreading center. That's not a spreading center. That's a transform fault. So that means that this North American plate is sliding along the Pacific plate. It extends actually down here into the Gulf of California. And then we get these little red bands here. Those are called spreading centers. So that's where we're creating ocean crust. So one plate, in this case, the North American plate, is moving away from the Pacific plate, and we've got new rock being created there. That's what's happening at Iceland too. It's also a spreading center, but it's above water. And then we have subduction zones. That's these ones with the teeth. You may have heard of like Mount St. Helens, Mount Rainier, Mount Hood. All of those are volcanoes that are created by this Cascadia subduction zone. Well, those are really exciting volcanoes, but we're not going to talk about those today. We're going to ignore those subduction zones. We're going to talk about transform faults and spreading centers that occur in the ocean floor. So we'll concentrate on areas like this. This is just a zoomed in image of that, which I already talked about, so we can kind of skip over that. We've got the spreading going on, and then the sliding. So this is the classic model of spreading and sliding, spreading, sliding, spreading. But turns out not everywhere in the world does it look like spreading and sliding and spreading. Some places it just kind of looks like spreading, and we don't know what's connecting it. This model that I just showed you here in the Gulf of California, here's a kind of a schematic of that. The red, again, is their spreading center. So the Pacific plate is moving away from the North American plate in this case. Then it's also doing that down here. Those two spreading centers are connected by a transform fault. And the transform fault is where they're just sliding past each other. Sliding past each other. So this is our classic model of spreading centers and transform faults. And we have earthquakes along those. So let's study the earthquakes. So the special symbol that we use for earthquakes looks like this. And this line through the middle is going to be the fault, the break in the plate that's between the spreading centers. Okay, so you might think, well, that's an awfully complicated symbol for an earthquake. Why did you choose that one? It also looks like a Secchi disk. Why would you choose a Secchi disk to represent your earthquakes? Well, it's because we use seismic waves to actually create this pattern. We look at the P wave, which is the first wave that's created when an earthquake happens. It radiates out from the earthquake, and then it is recorded at a seismograph. Well, that first wave either pushes the seismograph up or it pulls it down. And using that pattern of pushes and pulls, we end up with this pattern like a beach ball or like a Secchi disk. So it turns out, using that pattern of pushes and pulls, we get two options for the fault. Not just one, but two. It could be this one, or it could be that one. And then this means we've had a push at that seismograph. This means we've had a pull at that seismograph. Okay, so how do we tell which one's which? Well, in this case, we're going to say, well, geologically speaking, that one makes the most sense. So sometimes we can look at the local geology and say, oh, this is the fault plane. In other cases, we actually have to look at the spreading of the waves, like in a Doppler effect, to figure out which one's which. But in this case, we're just going to use the geology. We're going to assume that that is the fault plane. So we just went through, why not use like the symbol for the British use for some traffic sign. But we're not using this because this is actually created by the pattern that we record using the seismic waves. It's not just a random symbol that we picked. And if it's a stable geometry, and if this isn't changing at all, we're going to get a whole bunch of beach balls that look like this on this transform fault. Well, that's not the way it is going to be at every single spreading center. Instead, in some cases, we have a spreading center that's really got a lot of magma under it. It's really active. In fact, it's so active that it is going to extend itself down here. It's going to propagate like a crack going down into that plate. And then, oh no, this side's doomed. It's doomed to failure. It's going to fail. It's going to shrink over time, so that this is what it is now, but this is when it's going to be later. So that spreading center is now longer on one side and it's shorter on the other. So now, that's one scenario for that one. Another option, so we just established a nice fault is here for most transform faults. But what happens here is, does that transform fault just also move over time? Or does something else happen in this space? And so that's what the initial question was, is what's going on there? Let's use earthquakes to look at it, because earthquakes show us active deformation. what's happening right now. It turns out there's another option. Besides a propagating rift, we can also have something called an overlapping spreading center, which means that both sides are really super active, and they're both extending. Instead of one being doomed, they're both like, yes, I'm going to live. I'm going to keep going. I'm going to keep going. And again, what's going to happen in between there? Are they connected by a transform fault or something else? So we decided to test this using earthquakes. So is it like this, an instantaneous transform? That's one model. So we're going to have a hypothesis. Is it this model or is it this model? In this case, this is our propagating rift. This is our doomed rift. And instead of a single fault there, we have a series of faults. And those faults are all parallel to the direction of the spreading center, and then they curve. So this is another model, and it would show us a different series of earthquakes. So it would, instead of showing us this pattern, this beach ball, our beach ball would be rotated. So we can take a look at the earthquakes that occurred in the patterns that they create. It would also mean that not all of our earthquakes would be in a line. Here, they would all be in one nice little line. Here, they're going to be in this whole zone. So we have two aspects that we can test here. One, are the earthquakes in a line? Two, are the earthquakes lined up, perpendicular to our spreading centers, or is that fault curved? So let's do it. Let's figure out if there's a deformation zone, if they're spread out, and if those earthquakes are rotated. Either that's the fault plane, or in this other model, this other green one is the fault plane. Now you might say, well, let's just look at some bathymetric maps. Well, back in my day, there weren't bathymetric maps of these areas that we could look at to see what the faults look like. Do you have a question? Yes, some of them are more curved than others because this is the new propagating tip. It continually extends. And so that means here you've had spreading for a longer time and is going to curve it. It's either this one with one fault plane or this one with many fault planes. And they start out, here they're closer to the direction of the spreading center, here they're more curved. So if I said it opposite or didn't explain that correctly earlier, my apologies. This type of faulting we call bookshelf faulting. Imagine you have a bunch of books. Tilt them. That's what we're doing. Got a bunch of faults, and you're just going to tilt them in one direction, like on a bookshelf. So we have an instantaneous transport form fault or a bookshelf faulting scenario. So turns out these are the largest of the propagating rifts and overlapping spreading centers in the ocean basins. There are others that are smaller, but the small ones don't make earthquakes that are big enough for us to record far away. We'd have to be really right on top of it to record smaller earthquakes. So it turns out, of all of these locations, these two had the vast majority of earthquakes. So let's take a look at these two sites in greater detail, and then we'll look at the data from all of the sites. So let's start over here at the Lau Basin, which is in the Southwest Pacific. And when I say we, this is my student from the summer of 2024. And we took her research to the American Geophysical Union meeting in It was in Washington, D.C. this last December. And she's now in graduate school out in Oklahoma. She wants to go into the oil patch. So she's going to become an oil geophysicist. So a petroleum person. She's going to make a lot of money. She'll do well. So this is her poster, and I'm going to present the results of our work that she presented in this poster. Okay, so here's the Lau Basin. Here in pink is the propagating rift. So this side is growing, and this side is the failing or doomed rift. And now that we have really good bathymetry in these areas, we can indeed see that there are a whole bunch of curved faults. Some of them are curved a lot, and some are curved less. But we definitely do not see a single transform fault along this way. So let's take a look at the earthquakes. So the earthquakes also show that the deformation is in a large and a wide zone, rather than being concentrated along a particular fault. Concentrated in one nice line. Also, these are indeed rotated. And you might be like, well, how can I tell that they're rotated? You just told me they're rotated, but science, we need some data, right? Well, let's create a term, and that term shall be called the angle of obliquity. How much has our earthquake rotated relative to the spreading center? So we have the spreading center is 0 if we're aligned with the spreading center, or how much has it tilted compared to that? So here's our angle of obliquity. So here, this would be 0. This is going to be 10 degrees rotated, and then this one's 30 degrees rotated. So let's just see if they're all along the same direction or if they have a range of rotations throughout. There's 10 and 30 for our angles. Here are our earthquakes. And then what do? We're going to make a graph. Let's make a graph. So this is the number of earthquakes, and this is that angle. How much has that fault tilted compared to what we would expect if it were parallel or perpendicular to the spreading center? So you can see that there's a range of angles. So this would be if they're aligned to the spreading center, and this is more and more tilting away, and this is actually a negative tilt. We don't have, so clearly we have things that are tilting, and we've got a wide area that they're spread over. Okay, so then let's look at our East Pacific Rise location. This is actually an overlapping spreading center. So this is winning, but this side is winning as well. Neither side is doomed. They're dueling it out. And then we have this deformation zone in here for this overlapping spreading center along the East Pacific Rise. Okay, so here's the earthquakes. Here are the earthquakes. Again, these are our overlapping spreading centers. And again, we don't see an instantaneous transform. We see lineations in this direction. And indeed, we have a lot of earthquakes throughout this deformation zone. And if we do the same thing as we did before, look at the angle of obliquity of these earthquakes, we think we see two different populations. We see some that are in this northwestern region, and then some that are in this other region, and they have different angles of obliquity. So it appears that these earthquakes are being more influenced by this propagating rift, and these are being influenced by this one. Do we know that for sure? Nope. We would need to dig into the data a little bit more deeply. Maybe we'd have to go out and do a more detailed study of the area. This was just kind of a breeze through the data to see if we could show the same things that we saw 30 years ago. Okay, so I promised you I would show all of the information. Here's a big graph. So we still have number of earthquakes here, angle of obliquity here, and then we have the Lau Basin and the East Pacific Rise are the data that I already showed to you. And then these are the other smaller features. The Galapagos propagating rifts at 99 and 95 degrees west. And then there's one at 2.8 degrees south on the East Pacific Rise, as well as the Rivera microplate. So they all show a wide range of angles of obliquity. None of them are over here which is where we would expect for a transform, instantaneous transform. Okay, so that's where it would be for the transform fault. That's 30 degrees and then 60 degrees. So we had lots of rotation in these areas. So what have we learned? I like studying earthquakes. That's one of the things you've learned. Earthquakes are interesting. They tell us about the activity that's happening right now with respect to plate tectonics and even other places in the world that aren't along plate boundaries. Earthquakes at propagating rifts and overlapping spreading centers. We learned something about those features. We said that earthquakes reveal active deformation. And in the case of our propagating rifts and overlapping spreading centers, we have this broad deformation zone and we have rotated faults. And so basically our bookshelf faulting, this shows hardcover books. Our bookshelf faulting model should be more like soft cover books. You know, when you have a bookshelf of the soft cover books, the paperbacks, and they start to bend over. That's what we've got going on here. We've got a paperback shelf faulting model. And then, yeah, it's bookshelf faulting. And we've also learned that plate tectonics isn't perfect, right? We know that theories are things that we continually gain more data about and can refine. So the classic tale isn't perfect. Mid-ocean ridges evolve over time. After all, we know that plates move, they're created, they're destroyed, and this is all just part of that process. So we're improving theories as we gather and analyze more data. And with that, I'd like to thank you, and I'm happy to answer any of your questions. Sir.
I noticed that on the two plates, there are the two main ones, 29 degrees EPR and the Lao base.
The Lao Basin propagating rift is part of a back arc basin. It doesn't extend from the Gulf of California to the Antarctic plate. So the East Pacific Rise extends for a very, very, very long segment. Very long. Okay, let's see. Let me get my pointer again. I thought you wanted me to take the other microphone. That's not what you wanted me to do. Right. I figured that out after I took this off. So I'll get this pointer. And so the naming convention. The naming convention. All right. The East Pacific Rise is this whole section. So I used latitude to indicate where we were on the East Pacific Rise. There are a number of propagating rifts along there. The Lao Basin is this very tiny area here, and there's only one propagating rift in the Lao Basin. So I didn't need to specify the latitude. No, it's not your fault. It's a good question. Good question. Other questions? Yes. Oh. Sorry, I'm used to a much smaller classroom.
My question is, you talked about briefly the one earthquake that has been recorded to happen twice a year in Maine. Do you think that there's a chance that that is going to happen more often than 2 times a year in the future, like maybe even a long time in the future, but just in general? Or has it been recorded to just stay constant?
Okay, in the human time span, maybe in another 100 years, that rate should stay about the same. Long into the future, what's happening is that there's constantly stress along that fault. And so every time an earthquake happens, a little bit of that stress is relieved. Eventually, maybe over 1 million years, all of that stress will be relieved and we won't have any more faults. I mean, any more earthquakes along those faults if it just becomes a completely stable interior. So that's a possibility, is that They just peter out. I would not expect them to get more frequent, but things, yeah, I really wouldn't think that they would get more frequent. Other questions? Yeah?
Are the earthquakes in these spreading centers near the doomed rifts less common than near the propagating rifts?
So the question was, are the earthquakes more common towards the propagating rift compared to the doomed rift?
That's correct.
And so I don't think we saw that. And the first thing I think, what goes through my head is that it's hotter towards the propagating rift and cooler towards the doomed rift, which means that it's more likely for stress to accumulate towards the doomed rift because it's older and colder and has a greater chance to fault. But that's a really good question, and we could look at it more fully with both the data that we have as well as if we got more earthquakes along these propagating rifts.
Thank you.
Yeah, you're welcome. Good question. Yes?
Oh my God, sorry. It's really loud.
I know, it's disconcerting.
You mentioned that you spent a little bit of time in Iceland, and I was just there this summer, and a couple days after I
Maybe
landed,
we crossed paths.
yeah, maybe a couple days after I landed, one of the volcanoes erupted. So I
Yes.
got to see it, and it was really cool. But I was wondering if you are planning on doing any like future research there, because there's some really weird stuff going on in that town, Grindavik.
Yes.
Which is like crazy. I saw some of the buildings that they had, like it's completely deserted and there's like cracks in all the buildings. It's insane. And I was wondering if you like had plans or had ever thought about doing research there, because it's really cool.
I didn't have plans to do more research there because they have so many awesome geophysicists there. They have an amazing university system, as well as their meteorological society group is actually the one that oversees all of the earthquakes as well. So I have not thought about doing more research there. I would love to. With respect to the eruptions that have been occurring, it appears that they're moving into a cycle of increased volcanic activity. So they had a really dormant phase for a few hundred years, and now it looks like they're going to have a lot of volcanic activity. So look out for Iceland. There's going to be a lot more earthquakes and a lot more volcanoes. I wish I had been there during one of the eruptions. We did go to that town, Grindavik, and we saw the latest lava flow, but I didn't get a chance to see. A chance to see it erupt. That's too bad.
What's your favorite rock?
Oh, I get that asked all the time. They're all so good. How can you choose a favorite one? Now, my favorite, it's probably emeralds is my favorite mineral / rock. They're so cool. It's my birthstone. They're really expensive. They're pretty green color. They form in hexagons. I mean, I could go on and on about emeralds, but that's my go-to. That's my go-to. But I could tell you also about all sorts of rocks. I teach the class called Earth Materials at Eckerd, which is everything you wanted to know about rocks and minerals in a semester. So we look at rocks in hand specimen, we look at them under the microscope, and we learn lots and lots about rocks and minerals. So I can talk your ear about those. Excellent question. So let's go back to where we can see it. Oh, we can do it from here. So this Lao Basin scenario here, this one's propagating, and it's going to continue to propagate. This one's going to continue to lose, and so this spreading center is going to extend down until it stops. That's my thought. And it would stop at, I can't remember what's on the southern boundary. If it would it's either going to connect to the subduction zone that's over on this side. That's what's going to happen. It's going to connect with the subduction zone that's on this side. It's one of the fastest, deepest subduction zones in the world, called the Tonga-Kermadec Trench. So that's my prediction. It's going to join it. It's going to join the subduction zone. You have another question?
Yes, I do.
Yes, 60 years old.
You have stated that you were in the marine for a very long time. What has changed in plate tectonics?
So what's changed really about the science is computing power. So when I first did these studies, I had to digitize by hand all of the seismic records because they were all in like old-fashioned written on paper kind of thing. It was thermal paper, but you had these squiggles on paper, and then you had to take your mouse and click, 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 all over the place. And those seismic records originally came from microfiche. You probably don't even know what microfiche is. It's this thing that looks like a film negative. And it used to be where you stored books and reports and seismic records. So you would have to put it in this special reader in the library, find your record, print it out on this thermal paper, digitize the record, then use a program to take the seismic records and create those beach balls. Now those beach balls are automatically created within seconds of when an earthquake happens. Yeah. So that's literally what took me 3 years now takes a summer to recreate and to use all of the data from 1993 to the present day to just relook at all of those locations. Yeah, and you asked what's happened in terms of the science.
Let's rotate around for some other folks, because I think we've got a couple other questions also.
But it has been a lot that's happened, and we know a lot more about the hazards in the world.
So back to the Lao Basin with the propagating rift and it joining the sublimation zone. Would that just make it like bigger, or?
Oh, good question. So the Pacific Ocean started out as this little tiny plate. The Pacific Plate did, and then it grew bigger and bigger and bigger over time. So the question then would become, yes, the Lao, we'll call it the Lao, it's actually called the Tonga microplate right now. The Tonga microplate should then become bigger and bigger and bigger because the subduction is happening on this side. This is the Lao microplate. The spreading center is here. So this, you're going to get a bigger, 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 bigger plate because this is overriding this plate. This plate is subducting. So this microplate should become bigger and bigger and bigger over time. Yeah? Oh, that's a good question. Not that we're aware of. So these, what I didn't get into is that these faults are probably activated abyssal hills that are created along the spreading center. So as the spreading center spreads, rock comes up, but faults are also created. So those faults are stuck in the ocean floor, and eventually what we're saying here is that they become reactivated. They start to slip because of this propagating and dooming. So we don't think that they have an effect on the depth. These are all very shallow, certainly less than 10 kilometers. Yes, back there?
If you were to modify plate tectonic theory because you said it wasn't perfect, what would you add to make it better?
Well, in this case, what I added was that we have an additional way to connect two plate boundaries. So you can connect plate boundaries, spreading center, transform fault, subduction zone. So my modification was, well, we don't just have transform faults. We have these other diffuse deformation zones that are full of bookshelf faults. And actually, and this is a ramification of modifying plate tectonics, we're finding more and more plate boundaries that are diffuse. Plate boundaries that aren't just earthquakes along a line, but earthquakes that are distributed over a zone. So this is kind of a major modification of plate tectonics, is that we don't just have lines, but we have zones where deformation can occur. So it's not just a plate with just a well-defined boundary. It can be a plate with a very squishy boundary. Yeah? So this one is going to get longer, and this one gets shorter. So this deformation zone is going to extend. And eventually, like up here, there aren't any earthquakes. So eventually this area will also not have any earthquakes because there's no more stress in that particular area. Does that answer your question? Okay, great. Back there? Good question. So there are models for what happens into the future. And so we've got this cycle of a supercontinent cycle called the Wilson cycle, where all the continents are together and then they break apart to like where we are now. And then eventually it's going to all become a supercontinent again. And they call that Pangea Ultima is the next supercontinent. And here in the Atlantic, we're all spreading. It's all spreading. So the Atlantic Ocean is just getting bigger, except for a little tiny subduction zone near Puerto Rico down here. So that's getting bigger. If that one's getting bigger, what's happening to the Pacific? It's got to shrink. It's getting smaller over time. So Pangea Ultima, actually, instead of having these two pieces of the puzzle come together, the pieces of the puzzle are going to wrap that way. So the Atlantic Ocean is going to take over the world. That's the model. I think we have time for maybe one more question. Is that about right? Yeah. Gosh, what is the most? I should have stopped. I should have stopped before that one. What is the most recent discovery? Mantle. Oh, actually, lots. Thank you. There's so the mantle is indeed convecting like a pot of water. But what we're finding is that we have little blobs coming up, and those blobs, hot spots, come up and make hotspot volcanoes. So one of the recent theories, and I know there's others too, but one of the recent theories is that actually those plates that are subducting, they end up at the boundary of the core and the mantle. The subducting plate graveyard. And as those heat up over time, eventually, because those are made of oceanic lithosphere that started up here, they go down there, they heat up, and then eventually come back up as these hot, wet pieces of mantle, and they create the hotspot volcanoes like Iceland, like Hawaii, like Yellowstone, like the Canary Islands, the Reunion hotspot, all of these really, really cool hotspot volcanoes. So that's one of the more recent things. And we're constantly finding out more things about the interior of the Earth because we study that using geophysics primarily. And the more data we have and the better computers we have, the better idea we have what the interior of the Earth looks like. So that's one of them. Oh yeah, and then there's the diamonds there.
Right.
All sorts of stuff.
Lithospheric, like lithospheric delamination.
Oh yeah, yeah. Oh my gosh, there's so many cool things.
So I'm going to ask you one quick question just to sort of wrap up. And,
Okay.
And is there a relationship between spreading rate and angle of obliquity?
All of these are fast. That's a really good question. All of these are very fast spreading centers.
Yep. Very cool.
So.
All right. So, round of applause,
All
everyone.
right. Thanks so much for coming to hear me. I really appreciate it.